actually sustain that kind of self, weight, weight of its own, so that it doesn't creep or it doesn't fail. So there were, this is actually taken from some science fiction, but essentially the carbon nanotube represented a material that would actually be, useful for something like this. It's remarkable. But of course, imagination is one thing, actuality is something else, right? And when you start to engineer carbon nanotube-based fibers, it becomes not so good because there are interfaces that ultimately play a role. See, when you think about nanomaterials, the surface area to volume is very high. And whatever you do with these building blocks, we talked about Legos, right? But when you put them together, the interface plays a major role. Interface, in fact, dominates all the properties. So you need to understand and engineer the interfaces, right? So even after 20, 30 years of work in carbon nanotube area, you still don't have a fiber that is long enough or good enough to compete with, something that's represented here, or an excellent carbon fiber. You can't really compare because of the processing issues and so on. But that being said, there are a lot of advances that has been made. This is my colleague, Professor Matteo Pasquale at Rice, who has been spinning carbon nanotube-based fibers. And you can actually continuously spin these fibers. And these fibers could be useful for many, many things. In fact, the properties have been increasing with time, over the years. Now we're trying to improve this material property. Now we can get carbon nanotube fiber that are good enough for many applications, ranging from conducting cables to bioelectrodes. Right? So there's a broad range of applicability. So imagine that one day you are able to replace a metal with carbon in terms of the conducting fiber. Right? Metals are problematic in many ways. It corrodes, it's heavy. So there's all kinds of innovations that is happening in this space where such fibers could be amazingly useful. And people are also imagining things in applications from biomedical to technologies. At the other scale of things, there are also fascinating things happening in semiconductor industry. So the semiconductor industry is focused on shrinking size, right? You must have heard of the Moore's law, where everything shrinks with time. You make smaller and smaller devices, more and more powerful devices, lower power computing devices. So these are all paradigm shifts that is happening because you want to pack more and more devices so that your cell phone can be more powerful, your computers can be more powerful, right? So there is also a strong innovation happening in that space when things are very small. How do you engineer? And of course, your chip that goes into your computers is so complicated, so sophisticated that there are particular protocols that allows you to do these type of structures. But even a simple thing as a wire, a conducting wire, when it becomes very small, the metallic wires have significant problems. They electromigrate, they break, and stuff like that. But the idea was that you can actually think about something like a carbon nanotube-based structure for those type of applications. The other opportunity is to assemble large number of nanomaterials into a particular type of ordered assembly. So again, we talked about this. I mentioned about this Lego game. In the Lego game, you take pieces and put them together one by one, right? But if the piece is so small and the number of pieces are billions and trillions, how do you really do this? Right? You cannot just take one and put them, together. That will take impossible amount of time. So then you have to rely on something like self-assembly. How do I assemble large number of nanoscale objects in a particular ordered fashion? And how do I use that into a functional structure? Again, nature does this very well. That entire shell that I showed you before, it was all done through self-assembly. Right? Of course, nature has some very curious mechanisms where nanoscale structures are built and dissolved and so on and so forth, mineralized. But here, you don't have much of a choice. You have to assemble them large numbers together. So lots of people around the world are trying to create ideas and create approaches where you can assemble large number of nanostructures. Here is an example where we could assemble nanotubes in this fashion, like a cushion. Right? And nanotubes are made of graphite, so they are very compliant in the compressive direction. So you can actually get a foam-like structure that is highly compressible. And if you can do that, you can see applications. Recently CNT foams have been used for concussions and brain injuries. Right? So you can layer, for example, a layer of carbon nanotube forest on a helmet or something like that, which gives you very good shock absorbing property. So I think utilization of nanostructures into applications, all kinds of applications, are happening because you are able to not only make them, but also engineer them into the right kind of architectures. And this is what people like us do, engineering nanomaterials. Right? And that's exactly the essence of this talk. And there are many other applications. You can actually think about a miniaturized energy storage device that can be implanted as a medical device. Right? Power is important. Right? Power is everything these days, and you need the right kind of power, with the right kind of resources. So if you're thinking about a pacemaker, and of course you can put a battery, but you can make even better energy efficient devices. Right? So there are all kinds of interesting things when you're able to build these type of architectures with nanostructures. And then there are many other applications. This is thermal management application. If you think about the chip, the biggest problem is heat generation. Right? You can see your computers getting heated after you work for some time, right? And the heat has to be taken away. And there are again many interesting applications in that space using nanomaterials. Of course, assembly always gives you defective structures. So one of the things that is being proposed is 3D printing, because it's a bottom-up approach to building things. And you can create very interesting complex architectures by 3D printing, but the problem with 3D printing is that the scale is still not small enough. So you can print a 50 micron structure without a problem, but how do you really go to smaller and smaller scale? So this is another area that we work on. Here you can see that it's almost getting there, a few hundred nanometers. And direct printing and different types of printing will allow in the future to make structures not only complex, but also at the nanoscale. And there are other examples I will skip, alignment and other kind of approaches where you can get really highly ordered nanostructures that would be useful for many, many applications, including electronics, optics, and so on and so forth. So the bottom of the story is that you can really create highly ordered nanostructure-based architectures that would be very useful for applications. I mean, it doesn't have to be electronics or optics. It could be for a membrane structure, right? Water filtration. I think a lot of people are doing this, right? Can I create a highly ordered membrane with the right kind of pore size so that you can get perfect filtration? Now, there is another complexity. Most of the self-assembly techniques that people use give you two-dimensional assembled structures. Now, how do I build a three-dimensional structure where the nanostructures are really interconnected? Can I make structures like this? The answer is no at the moment, because it needs the tools that goes to that kind of resolution, but it's being, I suppose, developed. But we have done some work in that area, and if you can get three-dimensional architectures, highly porous materials with carbon nanotubes or other kind of nanomaterials, you can really do interesting things. This is another example where graphene, which is again a version of nanotube but flat, can also be interconnected to make these foams or scaffolds that could be useful. Could be again useful for biomedical, could be useful for filtration, it could be useful for oil absorption. There are all kinds of interesting areas where such porous materials, nanoporous materials, can be of use. And of course, if it's made of carbon, it has advantages of being highly conducting as well as temperature resistant. So the future is like this. How do I design and build materials with nanoscale precision? Right? Can I make membranes with the right kind of architectures, with the right kind of material, the right kind of dimensions? So the whole of materials nanoengineering paradigm is about understanding, designing, building, and characterizing, and then utilizing right later on. Let me skip a couple of things here, and then go to another interesting materials area, which is flat, super thin. So the nanotubes were like a wire, right, one-dimensional, and of course very, very tiny. But the two-dimensional materials are very different. They are also building blocks, but they are almost atomically thin and flat. And again, as I said, the graphene discovery was a very simple one, where they actually took graphite, which all of us know, and used the Scotch tape to peel one layer. One layer is essentially one atom thick. And then they were able to make a device from that one layer device and find some amazing physics properties there, and they got the Nobel Prize in physics. Right? So, I mean, sometimes even any lab in the world, if you are creative enough, if you can think beyond what is normal, you can make important discoveries. Right? I don't think you should feel restricted that you don't have many things around you to do things with. But if you're innovative, creative, you can think out of the box, you can do really fascinating things. I mean, even in our lab, we don't have expensive equipment really. But, you know, if the students can work together, think differently, you can really get to wonderful things. So the discovery of graphene is one such thing. They were just taking Scotch tape and peeling, graphite layer by layer. Anybody could have done this. Right? So, but again, for 2D materials, there are the similar kind of problems when you come to engineering. Right? How do I really build structures with the right precision and so on? So, I mentioned about these assemblies of nanotubes. You can make forests. What kind of assemblies can you do here? I mean, if I have, let's say, one layer, and if you have another layer, and if you have a third layer, what I could do is to put them on top of the other. I can stack them. So there are many materials in the world, in nature, that are layered structures. So graphite is a good example. The structure of graphite is such a way that you have very strong in-plane bonding, but very weak interlayer bonding. It's like a stack of paper, right? The paper is strong in the plane, but you can easily take one out, right? Because the interlayer bonding is weak. So you can think about materials which have different compositions for each of the layers. Right? So, for example, let's say I take 2 or 3 different layered materials, I exfoliate them, and then put them together, but not with the same material stack, but with different material stacks. So, similar to, let's say I take 2 decks of cards, and I'm shuffling, and I'm creating a new deck with, the shuffled cards. Right? So, can you do all these kind of things at the nanoscale? And if you do that, you can build totally new types of materials. And that's a fascinating part of nanoengineering again. So I'll skip again many of these things. You can make it in many ways. We grow these 2D layers in the lab. And again, simple equipment. It doesn't cost much money at all. I have a tube furnace which is operating at about 500 degrees centigrade, and I introduce a gas and it breaks down and forms a layer. I mean, these kind of experiments can be done anywhere without too much effort. And that's what I'm kind of saying, that some of the students here should be thinking about doing experiments with creativity and with limited resources. And of course, sometimes the characterization of that would be quite difficult, but that can be done with collaboration. Right? So think beyond what you have in terms of collaborating, and hopefully we can help as well in this. So let me again keep, we do a lot of work in the area of growth of these materials. We design experiments where we can grow these 2-dimensional structures in different ways, different geometries. So all kinds of things we do in our lab. Again, it takes another whole session to talk in detail about some of these things. But this is what I was saying, the creativity that comes out of simple ideas. So what I was saying is that you have all these Legos. In this case, each of these Lego is a sheet that has atomic thickness, single atom thick, or maybe 1 lattice parameter thick, right? And the question is, can I take some of these and stack them like this? Taking 2 decks of cards and shuffle. And if I shuffle, the material becomes completely different. So if each of these layers, let's say one is metallic, one is semiconducting, one is insulating, and I put all these things together, I get an entirely different stack with entirely different set of properties. And so many people today are actually looking at some of these engineering aspects where you can create new materials by taking these building blocks and putting them together. And when the building block is at the nanoscale, the interaction between consecutive layers are also very different and very interesting and strong, and people can find all kinds of interesting physics. And I will skip these, again, I make other devices as well, but what I wanted to show is another aspect that has come out as a very interesting one. So if I take a graphene layer and take another graphene layer and I put one on top of the other, I can change the properties by simply twisting one graphite layer on the other. And it seems that there are certain magic angles between these two layers that would produce amazing properties like superconductivity. So it's a different kind of engineering. You're not machining, you're not breaking stuff. You're taking two layers, putting them one on top of the other, and twisting. Right? So, of course, those things are done at the nanoscale, so the impact is quite different. Right? So there is a whole field called twistronics that is emerging, where you can really tune the electronic properties of materials by twisting at the nanoscale. Again, this is not, twisting is not really an engineering concept. Maybe, certain fibers and so on, but it's not a big thing at the macro scale, but at the nanoscale, you start to see significant property differences when you twist. And there are other materials like graphene. Boron nitride is another material that looks very similar to graphene, but is insulating compared to graphene that is metallic. And again, as I said, I can take insulating metallic layers, put them together, and I get something entirely different, which has never really existed in nature before. Again, growth mechanisms. I can actually design structures or domains within a single layer to make a device entirely on a layer that is single atom thick. So the power of nanoengineering, and again, nanotechnology is about manipulating things at the atomic scale. I can move atoms, I can move clusters, I can put them in place, I can make the right kind of interactions, and at the end of the day, I can change the physics of the system. So that is why the material science and nanoengineering is so fascinating, because the same material, if I organize differently, or if I move things differently, I get a different type of material in terms of properties. So that is what nanoengineering is all about. And again, more images. But I want to show this particular image. And this is a very colorful image. And this is a single layer of one of those 2D materials that I showed you. Right? It has these components. It has got molybdenum, tungsten, sulfur, and selenium. Right? And they're all kind of mixed in this layer. So if I create a material like this, how do I really understand what this material is? And that's why I said before, sometimes the instrumentation, the characterization becomes important. So this is actually a transmission electron microscope image that shows the position of every column of atoms in the structure. So today with the microscopes that we have, you can image every atom. You can not only image the structure, the location of that atom or column of atom, but I can also tell what element that is. So you can see the color codes, right? I can see where the sulfur is sitting on top of sulfur, again in a single layer. I can see where the sulfur is sitting on top of selenium. It's incredible. You can pretty much tell everything from the atom point of view. And this is again the power of the developments in material science, where you can, first of all, engineer these materials, but also tell the position of every atom so that you can control every atom in the structure. There's a lot of activities today on what is called single atom catalysis. See, most of the time we use catalyst, it's a cluster of atoms. And in most cases, only one or two atoms are really important. So how can I control that particular atom in that cluster so that I can control the entire reaction? I mean, in most cases, what we do is over-engineering. But when you go to the nanoscale, you can really do precise engineering. And that is what the world is going to, right? With atom precision techniques, you are able to control every atom in the structure so that you can manipulate whatever reaction it is you're looking at. So move on, final, just a few minutes. The nanocomposite is another area that we have worked on. The nanocomposite is mixing two different materials so that you get more than addition of those two systems. So there are many areas where composites are important. Right? The composite technology will one day replace big metallic structures, hopefully. It's already done in areas like aerospace. If you take the Boeing 747 or 777, most of the body is made of composites, not metals anymore, right? Because composites are, especially carbon fiber composites. So composites is very fascinating, and again, it is governed by these interfaces, because you have two constituents, and how the interface forms, how strong the interface is, essentially controls the nature of the composites. Here is another very simple composite, where it's an electrode for batteries. And if you think about it, the batteries that you use, it's a very complex system, right? It has got two electrodes, it's got an electrolyte. Within the electrode, there is carbon and the active material. You have a current collector. It's a composite system. How does this whole thing work together without actually deteriorating over 100,000 cycles? Right? It's really amazing how all these things work and how it has been optimized so that it works for you for a long period of time. Right? Another interesting thing about composite is the interfaces I already mentioned. Right? How do I engineer the interface so that the load can transfer, the electrons can transfer in the right way? So engineering interfaces becomes very, very important. Here is a very interesting idea that became commercialized. In fact, a student of mine who is in Manchester now was involved in this. Essentially, they added graphene material into a shoe that makes it much more resilient, much more robust, and maybe enjoyable when you walk. So again, there are frugal innovations that can translate to some very interesting commercial applications, and those are also the things that you should be thinking about as students. Again, the interface can really create materials that can be self-healing, that can be self-strengthening. Nature does a beautiful thing. I already started off with that, of the interface engineering, so that you can manipulate how dynamic properties change with time. And some of these things allude to that. Let me skip that. And again, composite materials is very complex sometimes, and you have to figure out what the functionality that you're looking for in order to optimize what you finally get. And here is an interesting. I started off showing this the shell, which has got these beautiful inorganic, organic composites. So in the lab, if you go about doing something like this, you can also create interesting composite architectures by mixing different things. In this particular case, we used a Kevlar fiber and a 2D material so that you can get the properties from the Kevlar as well as the 2D material. So you get high strength at the same time, high thermal conductivity or thermal stability. So the idea of making a composite is that you build structures which have multi-functionality, because the constituents in the composite offer the right kind of functionalities. But the problem is interface again. How do I manage the interface? Let me skip and I'll essentially end by saying that many of the things that we do in our labs are trial and error, optimization. But lots of things are changing today. There's also a huge computational power, AI, machine learning, that type of approaches that could guide you to get faster to the end point. Right? So today we work with people who are in the computational area, who work in machine learning and so on. The experimentalists and theorists working together so that you can not only just randomly do trial and error, but you can get some kind of guidance on where you want to go. So we will talk about combinatorial material science. And it's nothing but doing multiple experiments with the help of theory and other types of computational power. So again, the world is coming to a point where we are all collaborating. Material scientists are collaborating with biomedical people. The theory people are collaborating with experimentalists. Right? And all kinds of things are happening in the area of artificial intelligence. So I think it's a collaborative world, and that's a good thing, so that you don't feel lonely anymore. Right? You kind of go together. So, thank you very much, and that's my message.